Alright, so here's the agenda for the video. We'll start by defining what convergence in distribution means and convergence in probability means. Then we will look at the properties of convergence in probability. There are three important properties, starting with the fact that if xn converges to x in probability and yn converges to y in probability, then their sum and difference will also converge accordingly. Similarly, there is another property which says that if you have a continuous function g, then g applied on xn will converge in probability to g applied on x. And at the same time, the product of xn and yn will converge in probability to the product of x and y, right? We'll look at these properties of convergence, and then we will look at the relation between the convergence in distribution and convergence in probability, right? We will show that if a sequence of random variable has convergence in probability, then it will naturally hold convergence in distribution. After that, we will show the convergence in LP or the pth mean, which we denote by xn converges to x with an LP on the top. Along with this, we will also show the relation between the LP convergence and convergence in probability. So this is the agenda for the video. Let's get started. Let's start with the definition of what convergence in distribution means, right? Let's say we have a sequence of random variables xn, right? We say that xn converges in distribution to x if the CDF of xn, let me denote that by fnx. So this denotes the CDF of xn, right? This converges to fx, right? And this should happen pointwise, okay? It need not happen uniformly. So this function, so this is a sequence of functions, right? So this is actually a sequence of functions. Now this should converge to a particular function, and it should happen pointwise. That's it. If it happens uniformly, then well and good, right? But it should happen at least pointwise. This is the definition of saying that xn converges to x. So one more critical thing to note here is that fx need not be a valid CDF, right? It could be the case that fnx is converging to some function which is not a valid CDF, right? In that case, we cannot say that xn converges in distribution to x. Let us look at an example of that sort. Now let me define xn. Let xn have the following CDF. How does the CDF look like? We say that fnx is equal to 0 if x is less than n and 1 if x is bigger than or equal to n, right? So this ideally means that we have a CDF which is 0 throughout, right? It's always 0, but at the point n it rises and it becomes 1. So this is the CDF, right? Now in such a scenario, if I take the limit, so here if I take the limit of n going to infinity, fnx, I would obtain gx, right? Where what would gx be? Gx would be the identically 0 function, right? So gx would be 0 for every x. So this is a function which is identically 0. Now this gx cannot be a CDF, right? So we can say that this guy is not a CDF, right? So essentially the conclusion is that in such a scenario, we will say that xn does not converge in distribution to any random variable, right? So it does not converge, okay? That's what we conclude. All right, so that's all about the definition on the distribution convergence or the convergence in distribution. To be noted is that this is also sometimes referred to as convergence in law, and hence written as xn converges to x with a capital L on top, right? Next, let's discuss convergence in probability. Okay. So we say that a sequence of random variables, again xn, converges in probability to x if you give me an epsilon, a small positive epsilon, right? And I'm interested in the probability that the distance between xn and x, right, is more than epsilon, and this particular probability, as I increase the value of n, right, it will be equal to 0, right? So this essentially means that whatever be the epsilon that you give me, right, there will be a 0 probability that ultimately xn will be very far from x, right? So this means that xn is far from x, right? And the probability of xn being far from x will tend to 0 as you increase n, right? That is the idea. Okay. So that is the second point that we have covered, the definition on convergence in probability, right? Now let's look at the three important properties of convergence in probability. Or before that, let's discuss this important theorem which says that if xn converges to x in probability, then xn will converge to x in distribution. Alright, so let's try and prove this. So we will start by saying that let me take an x, okay, let me take a value x which is somewhere in the real line, right? And now I'm interested in the probability that xn is less than or equal to little x, right? I can write this as using the, using law of total probability. I can write this as probability of xn less than or equal to x along with x less than or equal to x plus epsilon. Let me take a small epsilon positive. Plus we have another probability term which is xn less than or equal to x with x being bigger than x plus epsilon, right? Now one thing to be observed here is that this guy is actually the probability of intersection of two events, right? So it will naturally be less than or equal to one of those events, which means it will be less than or equal to the probability that capital X is less than or equal to little x plus epsilon. By a similar logic, we can say that the second probability term will be less than or equal to the probability that xn minus x modulus is bigger than epsilon, right? Because, so why does this come about? This comes because this particular event that xn is less than or equal to x with capital X being bigger than little x plus epsilon is actually a subset of the event that xn minus x is bigger than epsilon, right? In fact, this event on the right hand side, this one, this is nothing but equal to the union of all such x for which xn is less than or equal to x and capital X is bigger than x plus epsilon. So thereby we can say that this probability term will be less than or equal to the probability that xn and x differs by at least epsilon, right? Now let's continue this. In the next step, we say that now we can bring the first probability term to the left hand side and say that the probability that xn is less than equal to little x minus the probability that capital X is less than equal to little x plus epsilon will be less than equal to probability that xn and x differ by at least epsilon. Okay, right? So now what is the terms on the left hand side? It is nothing but fn of x minus f of x plus epsilon less than equal to. So now we use the fact that we are starting with the hypothesis that xn converges to x on P, right? Now that implies that this term will be going to 0 as n going to infinity, right? So we can say that this is less than equal to 0 as n going to infinity. So before that, let me write another step and write it as limit n going to infinity fn x minus f of x plus epsilon is less than equal to 0. So we conclude that the limit of fn x is less than equal to f of x plus epsilon. Now we will do the same computation by taking a negative epsilon. So similarly, if we take epsilon to be negative, right? Or you can say, or let me write this as minus epsilon, right? Instead of epsilon, right? What we can say is that the limit of fn x is bigger than equal to f of x minus epsilon. So using these two equations, by putting or by allowing epsilon to go to 0 as much as possible, we can say that limit of epsilon going to 0 f of x minus epsilon is nothing but f of x, right? So in order for this to happen, what we do is that let's go back to where we started from, and instead of saying that x be an arbitrary real number, we will change this to say that let x be some point of continuity of f, point of continuity of capital F. So if we have that hypothesis, then we can directly conclude that this is equal to limit of epsilon going to 0 f of x minus epsilon is equal to f of x, right? And this guy is bigger than equal to limit of fn x. And by using the first equation, we can conclude that fx will be less than equal to by the second equation we can actually conclude that this is equal to fx and this will be less than equal to the limit of fn x. And from the first equation we can conclude that fx will be greater than equal to limit of fn x. And this implies, again, by taking the limit of epsilon going to 0, f of x plus epsilon. And it is here that we are using the continuity of f at the point x, right? So now I can say that limit of fn x is equal to fx, right? Which is same as saying that xn converges to x in distribution. So we have proved this particular theorem, which establishes a relationship between the convergence in probability and the convergence in distribution. Okay. Now let us look at the three important properties of the convergence in probability. So let me start by saying properties of xn converges in probability to x. So let us say let xn be a sequence of random variable which converge in probability to x, and similarly yn converge in probability to y. Right. The first thing we have stated is that xn plus yn will converge to x plus y. Again, the minus case will hold similarly. How do we prove this? For the proof of this, let's observe that the probability that xn plus yn is far away from x plus y by at least epsilon, this particular probability term has an upper bound of probability xn minus x bigger than equal to epsilon by 2 plus probability yn minus y bigger than equal to epsilon by 2. Now why does this hold? To understand why this holds, let's look at something. Let's look at first the triangle inequality, which says that xn minus x mod plus yn minus y mod is bigger than equal to xn plus yn minus x minus y, right? And this is bigger than equal to epsilon. So the event on the left hand side is same as this event, right? And that implies that this term is also greater than equal to epsilon. Now let me define an event A to be the event that xn minus x plus yn minus y is bigger than epsilon or bigger than equal to epsilon. And let me define B to be the event that xn minus x is at least epsilon by 2, and C to be the event that yn minus y is at least epsilon by 2. Now the idea is that A is a subset of B union C, right? Why is this the case? Because if we want A to happen, if we want the sum of this term plus this term to be bigger than equal to epsilon, then one of them should be at least bigger than equal to epsilon by 2. Because if both of them are less than epsilon by 2, then the sum will be less than epsilon, right? So we can say A is a subset of B union C. From here, applying simple basic probability theory, we can say that we have actually written this is probability of B, right? And this is probability of C. This is less than equal to. So this whole concept we have applied directly here, right? And now it's almost done, because if you look at this term, this goes to 0 and this term also goes to 0, right? And so since this is always bigger than equal to 0, any probability is bigger than equal to 0, so the required term will also, so this term will also go to 0, right? So that is the first property that we intended to prove. Now let's look at the second property. It says that if G is continuous, then G of xn, which is again a sequence of random variables, will converge in probability to G of x. That is the idea, right? Now, why does this hold? So to start off with this, let's first do one thing. Let's first understand that any random variable cannot have an arbitrarily large value with a sufficiently large probability. Okay, now this is a statement. Any random variable cannot have an arbitrarily large value with a sufficiently large probability. Now let me write that down mathematically. Okay, mathematically it means that you give me an epsilon positive, right? Give me an epsilon positive, right? I can find uh, a number k, right? So let me say k is a number which depends on epsilon, right? So k epsilon, right? Which is some real number such that the probability of mod x being bigger than k is less than epsilon by 2, right? Now, what does this mean? This means that if you look at the real line, say this is minus k, and here you have k, right? The probability that the modulus of the random variable x lies outside this interval is very small, right? Which means the maximum density is inside this interval. Alright, so let's continue with the proof. Now, actually we will now focus on this interval because we have seen that, okay, the maximum concentration or the maximum density of the random variable lies within this particular interval, right? So now we can say that in this interval, since we already know that G is continuous, in an interval G will be uniformly continuous, right? So we can write that G is uniformly continuous on the interval minus k to k. Now what does this imply? This implies that you give me again an epsilon positive. Let me use the previous epsilon itself. I can find a delta, right, which depends on epsilon and it also depends on k, okay, and this will be a positive number such that whenever xn and x, right, are close enough, are closer than delta, right, whenever xn and x are closer than delta, the corresponding value of gxn and gx will be closer than epsilon. So this is the whole definition of uniform continuity, right? Okay, and additionally we also have that the mod of x should be less than k, right? Because we want everything to happen in this interval, right? Okay, so now we can write this as so this can be thought of as an event, right? So now we can think of this as an event saying that mod x, now I'm shifting to the random variable x, right, less than k intersected with xn minus x mod less than delta epsilon k is a subset of mod of gxn minus gx less than epsilon, right? Now taking the complement both sides and applying probability, right, what we can say? We can say that the probability that gxn and gx are farther than k, farther than epsilon, right, is less than equal to, because we have taken the complement and then applied the probability. Here we will write probability that xn minus x is bigger than delta. Again, we'll have a plus sign because when taking complement this will turn into union, right? And then they are disjoint events, so we can simply add up the probabilities. And then here we can write probability of mod x bigger than k, right? Now we've already seen that this guy is less than epsilon by 2, right? And this guy will tend to 0 as n tends to infinity, because we've assumed that xn tends to, or xn converges in probability to x, right? So essentially we've seen that this will also tend to 0 as n tends to infinity. So we've proved the second property, which says that if we have a continuous function, right, then that continuous function applied on the sequence of random variables will have a similar convergence in probability as the original random variable xn. So the next property is that the product of xn and yn will converge to xny, the product of x and y, right? Now this is quite straightforward, right? So let me leave this as an exercise, right? In fact, this can be obtained by using the initial properties A and B, right? So this can be done. So let me leave this as an exercise, okay? Let's go ahead and discuss what is convergence in LP or convergence in the pth mean, right? So again, a sequence of random variables xn, we say that it can converge to LP to a particular random variable x if you look at the expectation of the absolute difference between xn and x raised to the power p, right? If this expectation goes to 0 as I increase n, then we say that this converges in pth mean, right? Now a very important theorem is that if xn converges in pth mean to x, then xn will converge in probability to x. So we see that this is a very stronger condition than the convergence in probability, and convergence in probability in itself is a stronger condition than convergence in distribution, right? Okay. In fact, the proof of this immediately follows from a very popular inequality known as the Markov inequality, right? So let me write that down. So Markov inequality, what does it say? It says that suppose you have a non-negative random variable, right? Then what can you say about the probability that that variable is bigger than or equal to alpha is bounded above by the expectation of x to the power p divided by alpha to the power p, right? This is the Markov inequality, okay? Now let us apply it here, right? We can say that we can write probability of xn minus x difference, absolute difference, being at least epsilon, right? This can be upper bounded by the expectation of the absolute difference raised to the power p divided by epsilon to the power p. Now, since we are assuming that this is convergent in LP, right, it means that this term will go to 0. But if this term goes to 0, then we can say that this term also goes to 0. And this would mean, so if this term goes to 0 as n tends to infinity, that just means that xn converges to x in probability. Right? So what we have seen essentially is that we have convergence in LP, right, which is a stronger condition than convergence in probability, and this is a stronger condition than convergence in distribution. So this is the setup that we have as of now. Probably in the next video we'll discuss another convergence type, which is convergence almost surely. Alright, so we had previously discussed a very important theorem which said that if a sequence of random variables xn converges in probability to x, then we can say that it converges in distribution to x, right? But we will see in subsequent videos that the converse is not true. But before that, let me state another theorem which says that xn converges in probabilities to some constant, say c, if and only if xn converges in distribution to c, right? Now when I say constant c, this can be thought of, so let me write that here. The constant c can be thought of as a random variable which is degenerate at c, which means that the probability of x equal to c is 1. It can also be thought of as a CDF, or a cumulative density function, having one jump at c, right? That's it. So it would look something like 0 everywhere, right? And at some point, say c, it will jump and it will become 1. Right? So this is how the CDF would look like, okay? Alright, so this is how we want to visualize a constant random variable, right? Okay, let's go into the proof. See, this part is already proved, right? In fact, this holds for every random variable x. So it will hold for c as well. We need to prove the other way around. That means we will assume that xn converges in distribution to c, and we will show that it will also converge in probability, right? Okay, so now let me write the probability of xn being far away from c for at least epsilon, right, to be equal to, so what is this? This is actually the complement of, so this is the complement of xn between c plus epsilon and c minus epsilon, right? So this will be the complement of, so 1 minus of fn of c plus epsilon minus fn of c minus epsilon, right? So now we can write this as equal to 1 minus fn of c plus epsilon plus fn of c minus epsilon. So as we increase our n, right, since we have assumed that the distribution converges, so this distribution, the CDF of c can be written as nothing but, so this is f, let me write f of say x is nothing but 1 if x is bigger than or equal to c, and 0 if x is less than c, right? So, or we can write this as the identity function or the indicator function applied on x bigger than or equal to c, right? So this can be rewritten as 1 minus, again, now if I take limit on both sides, so let me take limit on both sides, limit n going to infinity, this whole guy will be same as 1 minus, when I take limit, this will be nothing but fx, right, or let me write this as f of c plus epsilon, right, plus f of c minus epsilon. Now when I do epsilon going to 0, right, so limit epsilon going to 0, and then this whole guy will be equal to 1 minus f of c, because from on both sides the function will converge to, so from the right hand side, if you come, it will actually reach the value 1, so this will be equal to 1, okay? But on the other hand, if you come approach from the left hand side, it will be 0, so this will be 0. That means is nothing but 1 minus 1, which is equal to 0. So we have shown that the limit n going to infinity, so we have shown essentially that limit n going to infinity, probability xn lying far away from c by at least epsilon is nothing but 0, which essentially means that xn converges in probability to the constant random variable c.